Hi everyone, my name is McKenzie and I'm presenting our work on client-optimized algorithms and acceleration for encrypted compute offloading. In this work, we present a system known as client-aided HE for opaque compute offloading, or CHOCO. CHOCO is a system that enables privacy-preserving computation for resource-constrained devices. It does so by building upon existing homomorphic encryption and client-aided encrypted computing techniques. It enhances these techniques with novel client-optimized HE algorithms and additional hardware acceleration. These contributions dramatically reduce client computation and communication, ultimately making encrypted compute offload competitive with local compute. Furthermore, we show that these benefits generalize to diverse encrypted applications. This talk will be structured into 4 sections as shown. First, I will introduce our scenario and go through some necessary background on homomorphic encryption. Then I will explain our full system implementation before concluding with some results. Let's begin with the introduction. Resource-constrained devices are everywhere. These small devices operate within minimal power budgets up to a few hundred milliwatts and are often found in sensing applications, including health monitoring, environment monitoring, and infrastructure monitoring. If we take a closer look at one of these devices, we see that they are often used to collect sensitive data. This data is then processed to extract useful information and results. Naively, all of this processing would happen locally or within a trusted environment. However, these devices have a long history of decreasing in size, energy storage, and processing capabilities. At the same time, the amount of data being collected and the computation being performed is both scaling up. As this trend continues, it quickly becomes infeasible for sensors to do all of this computation locally. Compute offloading, or inference as a service, is one way to meet rising computation demands. In this scenario, data is communicated with a robust shared offload server and processed. Unfortunately, data privacy is the main barrier to realizing the benefits of offloaded computation. The client is forced to expose sensitive information in a potentially malicious environment. Thus, to protect the client's information, we need a way for data to remain hidden throughout the duration of this interaction. One way to achieve this is with homomorphic or fully homomorphic encryption. With that brief introduction to our scenario, we will now move into a little more background on homomorphic encryption. Homomorphic encryption is a way of processing encrypted inputs without ever decrypting them. Most modern HE schemes operate on vectors of data. These plaintext input vectors are sent through an encryption function, which uses a combination of modular arithmetic and the addition of random noise to obfuscate data into ciphertexts. We can then operate directly on these ciphertexts and decrypt to finally reveal a plaintext result. If everything is computed appropriately, this plaintext result will match the expected result from doing that same computation on non-encrypted inputs. Unfortunately, there are many challenges when working with HE, and if these limitations are neglected, that ciphertext may be made to become undecryptable, and those results will be lost. In the compute offload scenario that CHOCO targets, the client is responsible for the encryption and decryption of the private data, while the offload device is responsible for all encrypted operations. One of those encrypted operations may be the multiplication between 2 ciphertexts. Although this is a single encrypted operation, there are many underlying sub-computations. This is because each of these ciphertexts is constructed from multiple polynomials with thousands of coefficients each. So each of these operations is actually a polynomial operation with thousands of coefficients. It's then easy to see that the high computation costs are a primary challenge to the widespread adoption of encrypted computing. Another major challenge is the restriction to only linear operations. Homomorphic encryption allows for the multiplication, addition, and rotation of these ciphertext vectors, but that's it. Nonlinear operations, including popular activation functions like ReLU and tangent, are not directly supported in HE. Not only is the type of operations limited, but so is the depth. As previously mentioned, the encryption function adds some amount of random noise. Unfortunately, this noise grows with each encrypted operation, and if it surpasses some predetermined budget, that ciphertext becomes undecryptable. Therefore, encrypted computations can only perform a limited number of operations before needing to refresh the noise budget. Many of these limitations, specifically with noise growth and ciphertext size, are directly related to the parameter selection, which is application dependent and an ongoing challenge for even the most experienced application developers. Because of all of these challenges, offloading an entire encrypted application is still infeasible in many scenarios. In contrast, client-aided encrypted computing was introduced as an elegant way to overcome these limitations. To explain this concept, we look at it within the specific example of client-aided encrypted inference. In this scenario, the client has some input data, which it initially encrypts and sends over to the server. In fully offloaded computation, the server would take this data and complete the rest of the network using homomorphic operations on the encrypted data. In this way, the network would have to be designed to meet those previously mentioned constraints, specifically on the type and depth of operations. However, in client-aided HE, the server is only responsible for those computationally intense linear layers, which can be directly implemented using those HE multiplications and additions. It then sends the encrypted intermediate results back to the client, who performs decryption and can then do those nonlinear operations directly on plain text data. This back and forth interaction continues for the duration of the network. This style of computation has become very popular because it systematically limits the arithmetic depth and regularly refreshes the noise through those repeated decryption and re-encryption operations on the client. However, this also places more burden on the client than ever before. We quantify client responsibility by measuring computation time on an ARM Cortex-A7 CPU. Results are shown in this graph, which include the active client computation time to perform inference on 4 different neural networks. The left bar shows the time for client-aided encrypted inference using standard algorithms and the default parameter selections available in the SEAL homomorphic encryption library. This is shown in comparison to performing the entire networks locally using TF-Lite on those same unmodified client devices. We see that the client incurs substantial overhead to participate in the encrypted inference offload. Furthermore, this overhead is dominated by homomorphic encryption operations. It is exactly these operations and this overhead that CHOCO is designed to target. We will see that CHOCO reduces client-side computation by up to 341 times through both software algorithms and hardware acceleration. We can visualize these benefits in the context of a full system using this graph, which displays the latency for each distinct piece. While CHOCO reduces client-side computation, server-side solutions have also made tremendous progress. These solutions are complementary and necessary, but outside the scope of our client-optimized focus. Communication is the last piece and remains an ongoing challenge for many privacy-preserving protocols. While some overhead can be expected in favor of privacy, we will see that CHOCO reduces this overhead for client-aided encrypted implementations by nearly 3 times. With that baseline knowledge of homomorphic encryption, we will now get into the details of the CHOCO system implementation. CHOCO builds upon existing client-aided HE systems. It augments these systems with additional HE algorithm optimizations and client-side hardware support to benefit resource-constrained devices. We will start with the encrypted algorithm optimizations. As mentioned, we can perform a series of homomorphic operations to achieve some desired computation. This is what we would call the HE operation schedule, and it is the main part of algorithm development. However, because we're working with these encrypted vectors, we also have to consider the input packing and corresponding output unpacking of these vectors. So altogether, these 3 pieces make up a full HE algorithm. Although these algorithms are happening on the server, we're actually very concerned with them from the client perspective. Specifically, we're concerned with minimizing the arithmetic depth. In HE algorithms, the arithmetic depth is defined as the number of consecutive operations on any input. Again, each of these operations adds some additional noise to each ciphertext. Therefore, if we can reduce the arithmetic depth, we can reduce the noise growth, which allows us to use smaller parameter selections and subsequently smaller ciphertexts. This ultimately translates to lower computation and memory demands, and finally, less communication. These last 2 things in particular are directly relevant to the client. With that in mind, I'm going to present a novel optimization to reduce the arithmetic depth of a common computation, which we call windowed rotations. Again, HE ciphertexts store data as encrypted vectors. Windowed rotations are a common way of properly aligning the desired elements of different vectors to perform subsequent SIMD operations. Often, algorithms only need to align a subset of these elements. So ideally, these values would wrap around within some specified window of interest. However, in standard HE rotations, the whole ciphertext is being rotated. So this wraparound actually occurs at the beginning and end of these very large vectors. Because of this, achieving windowed rotations is actually a very difficult and expensive task. The standard way of doing them is through generic permutation operations. In this way, you start with your window of interest and perform an encrypted multiplication with 2 masking vectors to create 2 new ciphertexts. You then rotate these masked ciphertexts by the desired amount and add them back together to complete the full windowed rotation. You can see that this is incredibly expensive, both computationally because there are so many operations, and with noise growth because of that high arithmetic depth. To address this problem, we come up with the concept of rotational redundancy. Rotational redundancy is a novel way of packing input vectors with redundant entries on either side of the window of interest. In this way, you can perform just a single HE rotation. Those values get rotated in and ultimately produce the expected windowed rotation. By eliminating the extra multiplication and addition operations, this has significantly lower arithmetic depth and thus consumes significantly less of that precious noise budget. Because of the smaller arithmetic depth, we can ultimately use smaller ciphertexts and reduce client computation. The client impact of this improvement is added to our plot of active client computation time for encrypted inference with 4 different networks. On average, we see a nearly 2 times reduction in client-side execution time with these optimizations. Unfortunately, there's still a long way to go to meet that TF-Lite optimization goal. Therefore, we conclude that CHOCO algorithm optimizations provide a critical but insufficient reduction in client computation. We will see later that they also have a large impact on communication. For now, to overcome the remaining computation bottleneck, we turn to hardware acceleration. Prior work has presented FPGA solutions for both encryption and decryption. We find that this work accelerates some, but not all, of those client-side operations, still leaving significant overhead over TF-Lite. We recognize this deficiency for existing client-side hardware and develop comprehensive encryption and decryption accelerator, optimized for high performance with limited resources. We name this hardware CHOCO through Accelerated Cryptographic Operations, or CHOCO-TACO. CHOCO-TACO is a straightforward hardware implementation of the encryption function shown at the bottom of this screen. Following along with the equation, the encryption function begins with pseudo-random number generation from the appropriate distributions. These random vectors then undergo an NTT transformation so they can be multiplied with the public keys, which are supplied via an input buffer. The product then goes through an inverse NTT transformation before streaming to the polynomial addition module, where it is added with a second random vector. It is then finished off with an operation known as modulo switching. At this point, half of the ciphertext is complete and can be returned to the CPU via an output buffer. The second half of the ciphertext also undergoes the same processing, but it also contains the message which needs to be encoded. Encoding includes another round of NTT transformations, as well as some additional message scaling. At this point, the message is in a compatible form to be added to the second half of the ciphertext and complete the final ciphertext. Following this flow, we add a fixed data path through the hardware to perform the full encryption function. With a second data path and a few additional modules, the same hardware can also accelerate decryption. Focusing on one of these modules, we can take a closer look at CHOCO-TACO's hardware optimizations and design decisions. At the highest level, CHOCO-TACO is built from modules to perform all of the major subcomputations of encryption and decryption. Within each of these modules, specialized functional blocks perform specific operations. These functional blocks are repeated across multiple conceptual layers to process the multiple polynomials of a single ciphertext in parallel. The parallelism available at this level is directly dictated by the encryption parameters and is typically just a few layers. Within the functional blocks, individual processing elements provide substantially more coefficient parallelism. This is because there are thousands of coefficients per polynomial that are available to potentially process in parallel. Finally, tightly integrated memories are then added to each module to support this parallelism, as well as fine and coarse-grained pipelining across the functional blocks and modules. These memories allow us to store all intermediate results locally and minimize expensive data movement. In this way, we build up each of these modules from functional blocks and processing elements. To optimally allocate our limited resources, we vary the amount of parallelism and the supporting buffer sizes in a simulation-based design space study across 31,000 architectural configurations. Ultimately, we limited ourselves to a 200 milliwatt power budget, and then we chose the smallest design within 1% of the optimal time and energy. Under these constraints, our final hardware, as depicted in this diagram, can perform a single encryption in just over half a millisecond. That concludes the algorithm and hardware details of the CHOCO implementation, so we'll now move on to some final results and conclusions. Using the previously shown simulation statistics, we analytically incorporate our CHOCO-TACO ASIC accelerator back into our client-aided implementation. As expected, we see huge improvements over software alone, but let's focus in on these tighter comparisons. In addition to being much more reasonable for an IoT device, we find that the ASIC accelerator provides an additional 29 times speedup over the FPGA implementations. We see that this finally makes active client computation time of client-aided encrypted inference over 2 times better than local inference using TF-Lite. We can dig into this comparison with local compute even further by looking at both the time and energy comparisons across all 4 of these networks. Across both metrics, the blue bars show large client benefits for computation. Unfortunately, this isn't the complete story because it doesn't yet include communication. To estimate the end-to-end benefits, we study a reference implementation using Bluetooth communication, which we show with these additional yellow bars. With this implementation, we show for the first time that end-to-end client costs for encrypted inference offload can even be competitive with local compute using TF-Lite. It even displays end-to-end energy benefits for large networks. Although communication remains a challenge for future work, CHOCO has already made significant progress in this area. Through algorithmic optimizations, CHOCO reduces the amount of communication by up to 66% over that seal baseline. These improvements are even more impactful when compared to other privacy-preserving computation alternatives. This can be seen in this data set comparing just the quantity of communication. Across the y-axis, we see this metric compared for multiple different implementations of privacy-preserving inference using 2 sets of comparable networks. The contribution of this work is shown on the far left in the dark purple bars. For both cases, CHOCO sees a dramatic reduction in communication. For the most closely comparable implementation, we see a nearly 90 times reduction in the amount of data being sent back and forth. Furthermore, we even see large improvements over Lola, which is a fully offloaded, non-client aided implementation. Again, CHOCO is communicating more frequently, but overall it is using smaller and fewer ciphertexts. This is made possible because of our algorithmic optimizations, namely rotational redundancy. In the paper, we show that the benefits of CHOCO generalize to diverse applications. This includes unmodified DNN networks of arbitrary depth with arbitrary activation functions. We also show results for PageRank and encrypted distance calculations. Please check out the paper for these additional applications and many more results. In conclusion, this work motivates and prioritizes client-aware optimizations. Our optimized algorithms reduce communication by orders of magnitude over prior work. Together with our complete hardware acceleration, we show that this enables participation from resource-constrained devices in client-aided encrypted computing for the first time. Finally, we demonstrate the diversity of these benefits for several different encrypted applications beyond just machine learning. This has been a presentation of our work on client-optimized algorithms and acceleration for encrypted compute offloading. Again, we encourage you to check out the paper for more information. Thank you for listening.